Uh, Thank you for that. So, okay, this, as the name suggests, we're going to be talking about quantum fields, uh, which is basically what quantum field theory. So, let me just give an overview of the talk. We're going to start from the basics with quantum mechanics and how it fails. Then I'll introduce quantum mechanics very quickly. It'll be light speed. And we'll see how special relativity does not go well with quantum mechanics and how quantum mechanics has other problems, such as not having a good multi-particle system. And then we'll introduce QFT in a very relaxed manner and see how QFT can be observed by us in whatever sense. Right. So there's multiple ways to speak about to formulate classical mechanics. I think the most familiar way is Newton's e Newton's laws and his equations of motion with yeah, the three laws. Yeah. But we're gonna so there's this other formulation known as the Hamiltonian formulation, which I'll just briefly go through. So you express the energy as a function of the positions and momentum of each particle. Say, for example, for the harmonic oscillator, you have the energy is equal to p squared by 2m plus half kx squared. The kinetic energy plus the potential energy. And this, it turns out that your equations of motion, which are n second order differential equations. Okay, maybe I should wait for you to settle down. Yeah. Huh? Good question. I think that's a subject for another talk. Okay, right. So you have this function h of qi comma pi of the position and momenta. And it turns out you can re-express your the 2n, sorry, the n first order differential equations you had, which are q double dot equals so and so for a normal particle. In terms of these 2n first order differential equations. So you have a set of differential equations with qi dot dependence and pi dot dependence. A simple example, again, looking at the harmonic oscillator itself, you can see that these are equivalent equations of motion because this is just the definition of momenta. P equals mv and p dot is minus k by mq, which is minus omega squared q, the force due to a harmonic oscillator potential, right? Yeah. This function h of qi comma pi is called the Hamiltonian, but that's fine. Yeah. And these are called Hamilton's equations since they're derived from the Hamiltonian, right? Now, why is quantum mechanics bad? I mean, see, classical mechanics bad. So the first thing is photons. And okay, so the history of light, I'm sure some of you have heard about the Newtonian corpuscle theory and whatnot. So ultimately, what happened is Planck theorized that light appears in quanta of energies, as in each quanta consists of a fixed amount of energy, and the total energy can only be n times this fixed. It's sort of like a step. It's a energy step, and this energy step is h times nu, where nu is the frequency, and h is a new constant introduced by him called the Planck's constant. This explained various aspects of optical theory, such as black body radiation and photoelectric effect, which is when light hits a metal, electrons are ejected. So the classical theory has absolutely no way to predict this. And yeah, that the second reason being atomic spectra. So when light is incident on, say, some atom, and uh, the electrons, some electron in the atom absorbs this photon, or at least a part of it, the it turns out that this absorbed energy, which corresponds to some frequency, thanks to Planck's theory, and this frequency is proportional to 1 by n squared minus 1 by m squared, for where n and m are some natural numbers. Now, I mean, classical theory has absolutely no way to predict this. And this can, it turns out all of this, both of these, okay, at least the second one, can be explained by quantum mechanics. And I mean, you'll find out that this is actually what is called a change in the energy levels of an atom, where the electron transitions, say, from a higher energy to a lower energy, or vice versa, right? So let's talk about quantum mechanics. This is going to be pretty quick, so feel free to stop me if you have any questions. Right. So quantum mechanics essentially started when Louis de Broglie proposed the wave-particle duality, in which he hypothesized that waves, I mean, so just like how photons sometimes have particle-like behavior, electrons and other particles also exhibit wave-like behavior. And this was proven to be this was experimentally observed in the form of electron diffraction. So you pass electrons through a double slit, and you observe the interference patterns on the screen, and you get the same thing as light. The the yeah the the same as Young's double slit experiment. The same results are observed. So this was made precise by de Broglie later. He introduced this concept called a wave function. So what a wave function represents is not clear yet, in the sense de Broglie did not know what he was introducing when he introduced the wave function. All he proposed was that this wave function represents a particle, a free particle, precise to be precise. Oh, go ahead. Yeah. Uh, yeah, that's a good question. So, okay, so first of all, psi itself is a complex valued function. Yeah. Now, okay, maybe I'll go through it in detail. Uh, hmm? I'm sorry. Oh, okay. Yeah, it's fine. I mean, okay, so what De Broglie did was he looked at free waves in the sense, say, right, waves of this form, where these usually represent light. And I think, sorry. Oh, okay. Yeah. Right. And I think it's omega by k. Is it? Yeah. I think omega by k is the velocity of the wave. And this is, you can rewrite this as uh, v. And here the energy is thanks to, I just write C. Thanks to, okay, Louis de Broglie also proposed that since a particle has a wave-like behavior, its wavelength would be given by this. There is, I mean, some wavelength lambda, which is P by H. Yeah, yeah. So Yeah. So we have these two relations, right? And we can just, no, I'm sorry. It's something else, right? Yeah. Yeah. No, it's not. Like it's just for the photon. Yeah. Yeah. No, I think it's one by lambda. Yeah. Yeah. Okay. Yeah. Yeah. Right. Like h by p. Yeah. Now this implies the energy relation E equals PC, and this is for a photon. But if you're talking about a massive particle, say an electron or something in the non-relativistic regime, you would instead have E is equal to P squared by 2m, right? Now, so you can conveniently represent cos kx minus omega t and sin kx minus omega t as e to the I kx minus omega t. Is that fine? Yeah. And from this, how do you extract the energy? Uh, you can see that energy times t e to the I kx minus omega t is equal to uh, I times h bar partial derivative. Sorry, where I didn't understand. H bar, there's a bar on the H. Yeah, so H bar is H by 2 pi. Yeah, you're right. Yeah, so this you can see because dou by dou t brings in minus omega here. And oh no, I forgot. You might not know calculus. Okay, that's fine. Like, just think of these as symbols if you don't know. I don't know. Right. So similarly, momentum times e to the I so and so is minus I h bar dou by dou x e to the I so and so because of this relation. So yeah, k gets carried over, and you can see this is holding true. So in other words, this wave satisfies the wave equation, right? Because this is energy squared in some sense because there's two partial derivatives and this is momentum squared. So there's, yeah. So this basically E squared equals P squared C squared. That's all this equation represents. Now, if you want to generalize this for the free particle where E is P squared by 2m and not PC, what you would, what De Broglie thought would be appropriate is you take these operators and replace them here. So you have equals what's P squared by 2m minus, right. And if you recognize it, it's just the Schrodinger's equation without a potential term, right? Now, what Schrodinger did is just, you know, E is P square by 2m is true for a free particle. Might as well add a V of X here and took all the credit for it. Yeah. V is some potential. Say, for example, half kx squared minus alpha by r, something. It can be anything, some potential. and the particle lives in that potential in some sense. Right. That's right. Yeah. And now the next question to ask is, what does this wave function psi mean? And Born made the probability interpretation, which mean where he stated that the mod psi squared is the probability distribution of the particle, as in it. So uh, the probability of a particle being in a small portion dx uh, is mod psi of x squared dx. In the sense, higher the value of mod psi squared. Oh, 1 second. Right. Yeah. So higher the value of mod psi squared, the more likely the particle is going to be there in some sense. Yeah. In the sense. What do you mean by a time? Hmm. You're right. So the particle can be anywhere in space. We don't know where it is, but we do know what the probability of it being somewhere is. That's why we're looking at space. Okay. No, it's fine. Just ask questions. Yeah. Yeah. So that's what Born introduced, the probability interpretation. Uh, Nobody knew. Like they just assumed that it was actually the waveform of the particle, like the photon. But that's not a great interpretation because it had other consequences. Yeah, there's the development of quantum mechanics has like a lot of red flags, so to speak. But yeah, you shouldn't really dwell on it. Right. Now let's look at the free particle example. So we suppose that free particle has solutions of this form and got the free Schrodinger's equation. So so let's speak about the solutions. So they're of this form where it's e to the I px minus et by h bar. Oh, the nabla square is just and like a three-dimensional generalization. So here we had one position coordinate. You can have three position coordinates. So yeah. So yeah. So these are free waves with frequency given by energy and which also depend on momentum. And the wavelength is given by this, which satisfies, which yeah is like designed to satisfy De Broglie's wavelength relation. Now, simultaneously, Heisenberg came up with his theory of quantum mechanics known as matrix mechanics, where he said that each observable, such as position, momentum, energy, and so on, is represented by what is called an operator. In the sense, it acts on a function and gives another function, right? So, for example, in this case, the momentum operator is minus I h bar times dou by dou x. The energy operator is I h bar dou by dou t in some sense, although like, yeah. Uh, and so he observed that no matter what, uh, so to speak, coordinates you're in, position and momentum will always never will never commute. So you can see here actually. So the operator for position is just x times psi of x. You just multiply x to the wave function. Okay. Now you can see that if you first apply the x operator and then the p operator, and then apply the p operator and the x operator, you get this relation uh, that the commutator of x and p is I times h bar. In the sense, yeah, so xp psi of x minus px psi of x equals I h bar psi of x. And this comes from, say, calculus. Yeah. So, huh? Okay. Yeah. So x comma p commutator is just xp minus px as a, as in, yeah, this is how the commutator acts on psi. Yeah. And this is always I h bar, no matter what coordinates you're in. Huh? Yeah, so Heisenberg proved this inequality. It's called the Heisenberg uncertainty principle, saying, and this can be restated, reformulated in another way, uh, in which, okay, so you cannot measure position and momentum exactly at the same time. So delta x is the uncertainty in position, delta p in momentum. So you can never exactly know a particle's position and momentum at the same time. That's what Heisenberg states. You can know its position exactly, but then you wouldn't know its momentum at all. The uncertainty in momentum would blow up. So later, this Heisenberg's matrix mechanics theory was shown to be equivalent to Schrodinger's uh, quantum theory. Uh, yeah. So, yeah. So yeah. So measuring a position, particle's position first, and then its momentum is not the same as measuring a particle's momentum first and then its position. Okay, there's a bit of subtleties in this sentence, but I'll ignore those. Yeah. Yeah. So this just sort of summarizes what we've done till now. So the momentum operator is minus I h bar dou by dou x, and the position operator is this. It just multiplies the function with its argument. Now, yeah. So this is what Heisenberg proposed. And if you later on see, if you take the classical limit, you'll see that ultimately it all reduces to quantum mechanics. So it's hard to really explain how this makes sense. Okay, yeah, but yeah, fine. So yeah, so each observable is represented by an operator in the sense each observable is represented by some thing that takes functions and gives you a function. In this case, the position operator just happens to be f of x gives you x f of x in this representation. And the momentum operator is minus I h bar dou by dou x. And that's just how you can think of it as a postulate of quantum mechanics in some sense, like that the position and momentum operators are these, that they satisfy this relation and so on. Right. Uh, Now, we've spoken of the position space wave function. Similarly, you could ask, what's the probability of a particle having momentum p? And that leads you to the momentum space wave function, which is given by another complex valued function phi, which is a function of momentum. In this space, the position operator is given by I h bar dou by dou p, because Okay, yeah. But like, so you can make like a transformation, and it's possible to see this. And in this, mod phi of p squared represents the probability that the probability distribution of a particle being in momentum p. Uh, yeah. So, one. Any questions so far? Oh, yeah. So it all comes because the k here is 2 pi by lambda, and this 2 pi shows up everywhere after that. And so h bar instead of h. Yeah. Uh, Anything else? Right, I think I'll move on then. We'll start with, yeah, yeah, they are, yeah. Uh, yeah, so that's okay. So there is a symmetry, yes, in the sense they are Fourier variables. Uh, you can just make a Fourier transform and go from position to momentum and back. And in fact, the general scheme for quantization, canonical quantization, treats position and momentum on a very similar setting, because all that's fundamental is this relation, the commutation relation. And you can see there's no actual operator, explicit form of the operator. But yeah, uh, so you're right. They are like very interrelated. They are on a very similar footing. Right. Now let's move on to special relativity. Uh, So there's two main axioms in special relativity. The first being the speed of light is the same in all frames. The other being the laws of physics are the same in all inertial frames. Sorry, inertial frames. You're right. So now an important consequence is that no massive particles can travel at the speed of light. They always travel at speeds less than c. Now, yeah, okay, nothing. Uh, Right. Now, quantum mechanics violates this because if you look at the wave function, you will see that okay, suppose at t equals 0, 1 second. Yeah, so suppose at t equals 0, particle is at x equals x naught, right? Now, it turns out that for any t greater than 0, arbitrarily small, the the probability amplitude mod psi of x squared is non-zero for all x, which means in a really short amount of time, uh, it's possible for a particle to just show up somewhere else if you measure its position, which violates special relativity because the particle just traveled faster than the speed of light. Now, that's one problem. The second problem is that of particle creation, in the sense uh, you can have reactions such as electron positron giving you other particles, muons and antimuons. Now, what quantum mechanics is inherently particle conservative, in the sense you're implicitly assuming particles to be conserved because the argument of the wave function is just one particle, which is constant all the time. You're not allowing for the possibility of another particle to be there. And you may ask, okay, there's like two particles in either side of this reaction. What's the problem? Well, they're different species of particles, which is a problem. Yeah. Now, we can see how allowing for changes in particle number automatically leads to non-relativistic quantum field theories. Now, okay, let's talk about multiparticle QM first. So, yeah, yeah. Hmm. They won't, in the sense, okay, this is a good question. Like, so what comes into play is this thing called special relativistic velocity addition, in which there's like a different formula for addition of velocities. You can't just add velocities like you do in classical mechanics. What happens is you get, okay, I think I'll just write it down. So if a particle is moving at v1 and there's an observer at v2, I think the v1 prime is v1 minus v2 by 1 minus v1 v2 by c squared. So you can show that this is always less than c. It is, but everything changes a bit. It's a bit. It's not. No. Instead, it'll be this times the time interval. Yeah. Okay. This. Uh, yeah, they do, but okay. This. 1 second. Yeah, I don't want to go too deep into this because I'll end up explaining the whole of special relativity. Like we can talk about this later if you like. Yeah. Uh, yeah. So multiparticle QM. So instead of one argument, you have n arguments of particles. So each xi represents particle number I in some sense. Uh, and the probability density mod psi squared represents the probability that one particle is at x1, the second's at x2, and so on at time t. Similarly, you can speak of momenta of n particles, and that has the same interpretation. We'll use this notation, x1 comma xn ket, it's called. Uh, we'll represent the state of particles being present at positions x1 to xn by this, and particles being present at momenta p1 to pn by this. Like, yeah. And this wave function also satisfies the same Schrodinger's equation, which is a bit modified. You're just summing over all. Okay, there's an I there. Uh, yeah, you're summing over all the momenta of the particle, and there's like this potential which clubs all interactions of each particle, right? Now you can see that there's no scope of changing this number n because you're assuming that the number n is fixed. So implicitly, multiparticle quantum mechanics is uh, conserving the particle number. And we want to get rid of this axiom in some sense. So this is why we speak of creation and annihilation operators. So suppose you have like n particles with momenta p1 to pn. You can speak of some operator. You can define this object just just a mathematical object, which takes an n particle momentum state to a particle, the n plus one particle state with these momenta p1 to pn and k. We call it a creation operator because it's creating a particle, right? Now, similarly, we may define annihilation operators, which delete or annihilate a particle with a certain momentum k, right? And we'll also require this condition because you can't annihilate a particle with momentum k if there isn't a particle with momentum k. So this delta cube is sort of like it's non-zero only when k equals p and is zero otherwise. And it satisfies some other weird things. I'll not get into that. Right. So you can also talk about the zero, like the vacuum state, which is the state of zero particles. So using this, you may uh, represent any particle state using this relation. So you have like this state of no particles. You're creating a particle with momentum kn all the way to k1. And so you have an n particle state with these momenta. Is this clear? As in? Yeah. Yeah. So since we're talking quantum mechanically, you can't specify both the momentum and position because of the Heisenberg uncertainty principle. But you can speak of creating a particle with position x, say, for example. But in this case, you won't know the momentum of the particle because of the, yeah. Hmm? It's, wait, I'm sorry. To some accuracy, yes. Yeah. So, yeah. So, what you can do is create a particle with a wave function psi, so to speak. So you want to create a particle with wave function psi of x. Then what you would act on, and you have this n particle state, what you would act on it is this. So psi of x contributes to each position and with the probability interpretation. And so you have this where, so the ultimate uh, product is a n plus 1 particle state with n particles being at the positions x1 to xn, and the n plus 1th being at in this wave function psi of x. Is that clear? Yeah. Uh, it's, yeah. So like it represents the probability of the particle in some sense. So yeah. So we're creating a new particle, right? And this psi of x is it represents what probability density you're creating the particle with. Yeah, phi of x, the creation, the quantum field operator. Right. So this is clear, right? I hope. Yeah. I mean, not right now, no. Uh, Momentum need not be conserved since you're talking about literal particle creation. Like, no, this is just a purely mathematical formalism. So if you later on describe physical systems using this, such as particle reactions, you will require momentum to be conserved. So that comes into play later on. Right now, it's just some mathematical description. Think of it like that. Yeah. Yeah, you're right. Yeah. Because there's no other way to induce non-zeroness when k is equal to p. That actually causes a problem because that makes AK's operator valued distributions and not operators, if that makes sense. Yeah. Uh, yeah. So now that we've introduced these creation and annihilation operators, uh, you can see that the labels on each of these is x is a position or a momentum in the previous case. And there's, well, R3 many position and momenta. So what we're doing is assigning to each point on R3 an operator. Yeah. And that's why we call it a quantum field, because you have a field of operators. Okay. The why the word quantum comes is just because quantum mechanics also involves operators. And that's why, yeah. Uh, like three-dimensional space. Yeah. So you have three coordinates, each varying over the real numbers. It's how you describe our space in some sense. Now, what people normally do in QFT is something similar to canonical quantization, where they induce this non-commutativity in position and momentum. You require that the defining condition for a quantum mechanical system is that position and momentum are non-commutative. You can do a similar thing here, where you require that the creation and annihilation operators are non-commuting. Sorry, I didn't. Yeah, it's the same thing. Pi of x, pi of y minus pi of y, phi of x. Like, so it's basically the same as first creating and then okay, first annihilating and then creating minus first creating and then annihilating. Yeah. And this commutation relation is just like instead of, okay, there's a h bar here actually. I just omitted it out of habit. Uh, so so in the previous commutation, I'll just go back. Yeah. So while doing canonical quantization, what you do is that this ith components of position and momentum are non-commuting, while other ith and jth for I not equals to j is not equal to j do commute, is something we impose. But we do a similar thing for quantum field theory as well. Yeah. So we require that creation and annihilation don't commute only when they are acting on the same position, the same point in space, x and y equals, because this is zero if if x is not equal to y. And similarly for the momentum creation and annihilation operators, you have these, uh, that it's non-zero only when k equals k prime, when the momenta are equal. Yeah. So this is called second quantization by some people. It's a very bad name. A lot of people would agree with that. It blows up. Like, yeah, that's one of the problems with QFT. Like, yeah, you can't, because you have a continuous set of, like, the the label on phi of x is continuous, right? So you want the commutator to equal the I times the identity distribution. And in this case, the identity distribution is the uh, Dirac delta and not the Kronecker. You could, in the previous case, because you only had finitely many position and momenta, but in this case, you don't. So you don't have that luxury anymore. Okay. Now let's get to the meat of QFT, what it actually does. So it There's a way to induce Lorentz invariance in quantum field theory, which I'll not talk about, right? But instead, we'll talk about what quantum field theory implies in some uh, areas of high energy physics. So the currently the main motivation of quantum field theory is to describe particle reactions, where say an electron and and a positron annihilate each other, and so on. Now, uh, you can represent these reactions numerically using these things called scattering amplitudes, which tells you the probability that that a set of particles in the far past will collide and become this other set of particles in the far future. So, uh, if you expand this scattering amplitude, so to speak, what you do get is the sum of things called Feynman amplitudes, each of which are neatly represented by Feynman diagrams. So, for example, let's look at Compton scattering, which is uh, the where an electron collides with a photon and they both scatter in whatever manner. So these are two examples of Feynman diagrams which contribute to Compton scattering. So you could try interpreting this as, say, an electron is a photon is incident on an electron. The electron absorbs the photon, and then it emits another photon here, and they both scatter. One second. Yeah. Now, similarly, the second one shows the process where the photon is emitted first, and then the incident photon is incident, and the electron later moves out. So these are just Feynman diagrams which have some Feynman amplitude. So each of these processes has a certain amplitude associated to it, and the sum of all these amplitudes, at least formally, equals the scattering amplitude. Yeah. It's so you can ask how, but quantum field theory predicts it, and it actually has been experimentally observed. In the sense, it loses some energy, and that energy comes out in terms of a photon. It's something like, in daily activities, what uh, light is emitted, right? Energy is emitted in terms of light, in the form of light. It's similar to that, except it's spontaneous. Yeah, but it does happen. That is possible. Yes. No. Energy is conserved. Momentum is conserved. Yeah, but the electron will lose energy. The combined energy of the electron and the photon must equal the energy of the initially incident electron. Uh, it it will, and then it reaches the beam of light after being scattered once, and then it scatters again after absorbing the photon. Yeah. So uh, so you can look at uh, what do you mean by a particular point? Like it could. I mean, so you can. So okay, if you actually write down the Feynman amplitude, you'll see that the point of scattering doesn't really matter. Like the the position variable of that point is actually integrated over. Okay, like each. Okay, I'm not sure what you're trying to ask. Uh, in the sense, okay, fine. I mean, we can talk about it later. Yeah. Like, there are problems with interpreting it as actual scattering problems, like as an actual scattering process, because you also have diagrams like this. Okay. Oh yeah. Okay. That is possible. Okay, that's what you meant. Okay. Yeah. 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 So that's a good question. Like, I mean, so what this tells us is you can't actually think of each diagram representing light actually turning around and moving in such a path, so to speak. Uh, it's just a representation of the amplitude, and you can. Uh, so this example just serves as a serves the purpose of telling you that you can't think of scattering as just particles going on trajectories anymore, because uh, there are more complicated things happening inside this scattering black box, so to speak. Like, there are way more complicated diagrams. You can have such a loop. This is called a loop. You can have such a loop coming anywhere, and like a photon being emitted and reabsorbed by the same electron. And yeah, but each of them has a contribution to the amplitude, to the process, the probability of this process even happening. Like two electrons, like an electron and a photon colliding to give an electron and a photon. It is, yeah. Like, there is an algorithm. Like, you have these vertex rules, which is given by the interaction of the quantum field theory. After which, so for example, this here, there's the vertex rule being employed is an electron can emit or absorb a photon whenever it wants. There are other vertex rules, such as an electron and a positron can meet to give two photons or even one photon and stuff like that. So that's part of the mathematical theory behind it. Like, yeah. And you can calculate parts of the whole scattering amplitude. But the problem is there's a lot of Feynman diagrams you can have. So this is just one loop order. You can have any number of loops. And so, for example, you have a photon here, right? In the middle, you can have an electron and anti-electron pair popping up and getting annihilating each other again to produce a photon. That's completely possible. You just have another loop in the process. You can have such a thing in the middle of this loop, and that's allowed. So so as you increase the number of loops, the number of diagrams gets increasingly, the number of diagrams also increases very rapidly. You have infinitely many diagrams, yeah. Like, hmm? So it's like a series, so like a perturbative series actually. You just look at the first few terms and yeah. Big, I mean, okay, you mean the just the momentum because you can't get both. Yeah. You will know the momentum of the photon, yeah. Uh, okay, so suppose an electron is incident here. The photon is emitted by the electron. Now, this photon can have any momentum. Like, no matter what momentum it has, it nothing is contradicted because it's reabsorbed by the electron here. So the electron exits with the same momentum, and momentum is conserved. The shape of the loop doesn't matter. Only like the fact that there is a loop. That's the only thing that matters. Like, are you talking about like the squiggly nature? Huh? Yeah. Like this squiggly doesn't actually represent the photon's trajectory by any means. I mean, what I'm saying is the diagram itself doesn't represent any classical trajectory you can think of. It's just some process which whose amplitude can be represented as a diagram. Yeah, it is possible. Yes. Yeah. So that can happen and energy will be conserved at the end, but the probability of that happening will be very low. So it will contribute a very small part to the scattering. So I think you're talking about something like this, right? I'll just draw the diagram. So you have an electron, something like that. Yeah, okay, that's just some representation. Like, yeah, they are going in some, they'll have momenta such that if this is k, k plus, k minus, k will equal k plus plus k minus. So the total momenta, the momentum of the electron and the anti-electron and the positron will be the same as the momentum of this photon, if that's clear. Yeah. So you can have such diagrams. In fact, you can have like another loop in the middle of this and it's allowed. So it's just that the more loops you have, the less the diagram contributes to the amplitude. Because, yeah, usually, yes. I'll, yeah. So those diagrams are called tree level diagrams, which have no loops at all. And those contribute more because there's less interactions going on. Uh, if you take h bar going to zero and c being small, you get classical, yeah. So yeah, I think loops have a factor of h bar, while tree levels usually don't. Yeah. Now let's talk about the standard model. Uh, so the standard model is this theory in quantum field theory. Do I have time? Much more time do I have? Yeah, I'll be done. Right. So the standard model is this theory which describes almost every interaction known to us. Uh, this includes the electromagnetic interaction, the weak nuclear force, the strong nuclear interaction. It doesn't include gravity because gravity poses some problems, which we'll get to later. So for each interaction, you have a mediator and a list of particles which interact through this interaction. So for example, the electromagnetic interaction is mediated by the photon, and the strong interaction is mediated by these particles called gluons, which behave very similar to photons, but they have color and different interacting terms. They interact with what are known as colored particles, such as quarks and so on. And photons interact with charged particles, electrically charged particles. There's the third interaction, which is the weak interaction, which is mediated by the W and Z, the Z bosons. And yeah, they usually help in nuclear reactions as well. They are, yeah, they just happen to be. It's not, no. Like you can have like uh, composite particles which are bosons but aren't mediators. But among elementary particles, all mediators are bosons and all bosons are mediators. And yeah, there might be, I haven't heard of any. Yeah. There's also like the Higgs boson, which has recent, yeah. Okay, yeah. So the electroweak theory just unifies electromagnetism and the weak theory by uh, certain means. I think even I'm not like very knowledgeable about it, but yeah. So I think in some low energy limit, electromagnetism and weak force tend to separate from each other. You can actually distinguish between the two. But in the strong energy regime, uh, photons and the WZ bosons have very similar interactions, and you can sort of represent them together. That's what that is. It is possible, but we haven't observed any. Yeah. Yeah, yeah. That's great. Yeah. Uh, where was I? Right, the Higgs boson. Yeah, so the Higgs boson is this additional boson which induces what is known as spontaneous symmetry breaking. And recently, at least like 20 years ago, it was this has been theorized to, in some sense, create mass through this symmetry breaking. And yeah. So when you speak of a symmetry, you can like a symmetry is this transformation under which the your uh, your I don't know equations of motion are the same. Okay, no, we're not. Okay, that is an example, and in fact, yeah, I think that is the symmetry, like PT symmetry. P and T symmetry, P or one of them. So if you say switch position, like the space-time coordinates, I mean space coordinates by it, multiplying it with the minus sign, I think the solution changes, but the equations don't. So you have another solution, but the equation of motion is still satisfied by this new solution, and that's called spontaneous symmetry breaking. Yeah, something. Yeah, I think. I mean, uh, it's so it does matter in the sense that somehow induces a mass. I'm not sure about the details myself, but yeah, uh, right. This is like the list of particles. I think this is like a standard Wikipedia image. Yeah, so you have quarks and these leptons, and the bosons here, which are the mediators, these are the mediators of the interactions, and this is the Higgs boson, which is separate. This is an example of a Feynman diagram in the standard model. It's so you have like a bottom quark coming, bottom colored quark, which interacts, which splits into a W boson and a top quark, which interacts with this electromagnetic field with this photon and gives you a strange quark at the end. So this is an interesting Feynman diagram because in some regimes it gives you a significant contribution to the amplitude, even more than tree level sometimes, and it gives some insights on symmetry breaking and CP symmetry. Apparently, yeah, uh, yeah. What it does is okay. So if you look at it naively, you have a target, which is say an atom or something, and you have a beam of particles which are shot on it, and this beam of particles interacts with the target, and some product particles are scattered, right, in different angles. So you just measure how much of each particle, the number of density of each particle at each angle here. I'll give a figure. Yeah, I have a figure. Nice. So you have like this beam and this scattering center or target, and it reacts with that center, and you get these particles which get scattered. And you can look at an angle theta and see the number density of each particle. And this directly corresponds to the scattering amplitude in uh, and this is how physicists measure scattering amplitudes, so to speak. And this is how people verify the standard model, and by looking at the sum of Feynman amplitudes and equating them to the scattering amplitude they actually found experimentally, and so on. Yeah. A nice picture to have in mind is the Rutherford scattering. You have like this gold foil, alpha particles, they get scattered in all angles. And you have this detector, right, zinc or something. So you want to measure the number density of alpha particles at each place. And that's basically what Rutherford's experiment is. Yeah. Uh, I'm sure there are. I can't think of an example immediately. Yeah. Uh, oh yeah, neutrinos are a problem. Like we have nobody has been able to figure those out. Uh, so uh, neutrinos haven't we so they have very small mass if they have any, and we haven't been able to model them using any kind of fermionic theory. So that's a problem. Yeah. Yeah. So that's yeah. So that's an estimate. We don't know actually how much it actually is. Uh, it might be smaller than that. You never know. I mean, maybe we might know in the future when experiments are made more precise and we actually observe neutrinos more often. Yeah. Right. So uh, I'll finish the talk with this. Just a few comments about QFT. So the first thing is quantum field theory has a lot of infinities, in the sense there's a lot of infinities that just show up. Most of these are because of the Dirac delta in the commutation relation. And So for example, if you look at vacuum and try to measure the energy in vacuum, you'll initially find out that it's infinite. The energy density is infinite, which sounds ridiculous, but yeah. So there's this entire subtopic called renormalization. There's also regularization, which deals with these infinities and tries to find finite numbers from it. Uh, so that's one thing. The second thing is quantum gravity. So gravity does not go well with QFT. This is because gravity is not renormalizable. In the sense, there's infinities you cannot remove from uh, any quantized gravity picture you have, which uses QFT. And the solution to this is just finding an alternative theory which unifies quantum field theory and gravity and reduces to them in appropriate limits. One example is string theory, but it's not been experimentally proved. So, but what one could do is look at this non-renormalizable gravity in, say, the low energy regimes and extract observables from it. This is known as effective field theories, where you just ignore the high energy, non renormalizable parts of quantum gravity and look at the nice parts of it. It sounds like a scam, but it apparently isn't. Right. You can, yeah. So it does, yeah. So, for example, the standard model is technically an effective field theory because gravity is sort of integrated out. You're just ignoring gravity. So if you're looking at the rest of the interactions as an effective field theory. Yeah, that's literally what it is. Yeah. It's the term is integrating out the higher energy regimes or what something. Yeah. So you're integrating out the gravitational interaction, and what you're left with is the other three. And that's what leads to the standard model. If you further integrate out the weak and strong interactions, you're left with this thing, quantum electrodynamics. Yeah. And yeah, the third thing is there are a lot of Feynman diagrams, like I said. To each process, there are like a lot of Feynman diagrams. For example, there is like the simplest of all theories, the scalar phi cube theory, has Feynman diagrams of the order n minus second Catalan number or something for endpoint scattering. And that's a lot, which is like, it's like to the order 4 to the n. And that's a lot of Feynman diagrams. So we want a way to compute these amplitudes without actually having to calculate each Feynman diagram individually. There are a lot of proposed regimes for this. One of them is the amplitude-hedron program, where these amplitudes are represented in the forms of uh, these nice polytopes called the amplitude-hedron. Uh, People at IIS Princeton are working at it right now. It's actually interesting. Right. So, yeah. Uh, is there a question or I guess not? Right. But are there any questions? Because I'm more or less done. Oh, yeah. Uh, we can do that later if that's fine. So it like agrees with experimental results very well. The standard internal okay, there are a lot of inconsistencies. So first of all, the quantum fields you speak of, they aren't exactly operators. They are operator valued distributions. And you can't multiply them. You can't speak of phi of x times phi of y when both of them are distributions. And that's like the most immediate inconsistency in the sense it doesn't mathematically make sense. Now, there's mathematicians who are looking at models such as topological quantum field theory and so on, which are rigorous, but I, I don't think any physically realizable topological quantum field theories have been worked with yet. And yeah, so that's one thing. The other thing is non-renormalizability and like other physical problems, but I think those are few in number. So like numbers wise, standard model agrees very well with real world experimental predictions. Yeah, but it is mathematically inconsistent. Any other questions or? Yeah, I mean, if there's no other questions, we can finish it. Yeah. Yeah.